All right, let's go ahead and get started. Thank you everyone for coming to this month's Tulsa Lambda Lunch Meetup. All right, so thank you for joining us. We're here thanks to Techlahoma, our volunteers, and our speakers. Techlahoma is a nonprofit volunteer-run organization that puts on 32 groups, 2 conferences, and sponsors free local events. We do all this to support the grassroots tech community of Oklahoma. Learn more at techlahoma.org. Also donate at techlahoma.org. If you want to get more involved with Techlahoma, you can go to help-wanted.techlahoma.org to find out ways that you can volunteer. There is a GitHub repo with issues, and you can go and figure out some way to assist the community. All right. We've been streaming all of the OKC-based user groups to twitch.tv/Techlahoma. If you have an Amazon Prime account, you can subscribe to the channel free every month. Techlahoma gets a small donation from Amazon for each subscription. So if you have Amazon Prime, you can help Techlahoma out in that way. 36 Degrees North donates the space for us to meet. They also offer free workshops as well as co-working, desks, and offices for a monthly fee. You can find more info at the front desk. And finally, thanks to our food sponsor, Tech Systems. I want to also note that Zealcon is hiring, so if you want to work with me and do functional programming, please go to our website. All right, with that, today's talk is F it all, a higher order of reasoning. Now, I want to preface this that I have lots and lots and lots of slides. So if I have to do a part 2, I will. But if you have any questions, stop me at any time if I'm going too fast. I like to be interactive. I'll try to remember to repeat the questions for the live stream. So, all right. Try to do my best narrator voice here. You are entering the vicinity of an area adjacent to a location. The kind of place where there might be an effect or some kind of weird lens. These are just examples. It could be something much better. Prepare to enter the functional door. As per your request, please find the enclosed, the last man on Earth. Finally, solitude. I can write software for all eternity. Drops glasses. It's not fair. So I ask, why might he be the last man on Earth? Anybody see something wrong with this? Anybody? We launched the nukes, making them the last man on Earth, maybe? All right. Okay, so we can see here in our add to function, we are printing a line, right? What about here? So we have this do thing 1, and we have this add to function. Do thing 1 just takes an int, returns unit, add 2, takes an int, returns an int. We have this variable up here, and we just innocently call add 2 when we get 25, and that's great. Then we do thing, and then we do add 2 again, and suddenly nuclear bombs. And not good, right? So what's the problem? Also ask yourself this. How many times have you had code with a similar error, where you just innocently called a function that did one thing last time, and now it totally does something else, something unpredictable? So the function is doing something not obvious from its name, and the types don't give us any clue what it's doing. It takes an int and returns an int. Why did it launch nuclear missiles everywhere? So the problem we're talking about is effects, and they're everywhere. They're console output, writing and reading from a database, mutating state, interacting with the world outside of your program, starting world wars. They're everywhere.
It's all the reasons we write programs.
So this, hey, I need effects to do real work, not just starting wars. My program does nobody any good if it just makes my CPU warm. You might be saying. So we can't just get rid of effects, but what can we do to try to make it more obvious what our functions are doing? So let's consider making maybe a signpost or some sort of signal to tell us, beware, there be dragons. All right. So we're going to call this signpost IO, and we're going to give it a few functions just to make our life easier. And those functions are going to be map, giving us some way to transform a value inside of our signpost, and flat map, some way of marking that we're going to continue doing more dragon and nuclear war inducing things. So you can see here, we have this unsafe run inside of our IO. And we have this, I can't highlight over here. We have this unsafe run, and it's just a function that returns A. But this is our warning to our future selves when you go look at this code that our thing is going to do bad stuff. So here's a couple more examples here just of ways we can build it. So we can suspend some effect, we can delay creating the value A, and we can just stick a value A into it. Let's see what this gets us. So we're still going to do bad stuff, but now we have this important notifier here, this IO, to tell us this thing does something besides just nothing, because unit is nothing. And then this add 2, we're going to take in some integer, and we're going to do something besides return a unit. We're going to perform some sort of effect. So now we have a signpost to ourselves, a warning that dragons are going to happen. So we're going to use that delay, and what delay does is it says, don't execute this block until I absolutely want to. You can see we're doing exactly the same kind of stuff internally that we were doing before. So now we do our add 2, like we did before. I tried to do thing, my signpost activated. I can't just operate on the integer, because now I have a warning that I have some other type, that I have to be aware of the dragons that I'm dealing with. So we're going to use in Scala this feature called a for comprehension, which is just a fancy way of using those maps and flat maps so you don't have to do terribly nested stuff. Has anybody here used async await with promises in JavaScript or C# or anything else? You can think of it as a similar pattern. Async just does this in a way that's more familiar with imperative programmers. So now we're going to add 2 like we did before. We're going to store that in R1. We're going to do a thing with that R1, which returns nothing useful. We're just doing it for the effect. Then we're going to add 2, and we're going to yield that result, and we see that our program hasn't done the thing yet until we execute the unsafe run. So now you can see this is when the nukes are launched. So the point of this is when you call this function, you can call this program function as many times as you want, and bad stuff isn't going to happen until the caller wants the bad stuff to happen. They can compose it with many other side effectful functions, and they can encapsulate that to only run at the end of the world, as it's often referred to in functional programming. That is the top level of your application. Importantly, we're forced to recognize the effects and deal with it. Okay, but my slides are a little messed up here. But what did we really get for all that work? We got pure functions that are referentially transparent. The thing that I said where we can run program again and again and again, and the bad side effect stuff doesn't happen until the caller wants it to happen. So a referentially transparent function is an expression that's called referentially transparent if it can be replaced with its corresponding value without changing the program's behavior. So any questions on the whole effect thing that I just covered?
So like in if you had an API, you would want the bad stuff to happen at the point that you're computing the result, the send,
So the
to the caller, and all of your like logic below that would just be composing this thing you want to do, and then you want to actually execute it.
Yes. So we have we're allowing ourselves to give the control back to the person who called it. This is like the difference between doing something eagerly and doing something lazily. For example, if you've used promises or futures, when you're given a promise or you're given a future, they're already happening. So whoever you're handing that to has no control about when that thing happens since it's already started. They also can't repeat that operation. They can just get the value. But if you're doing it lazily, then it doesn't happen until the person who, the caller, the person who has that value wants to compute it, and they can recompute it over and over again from that IO value. So let's say you wrap the IO, you're wrapping like random.nextInt in an IO. That IO, if you call unsafe run, will always give you a new random value. Unlike if you wrap random.extent in a future, you'll get the exact same value every time you ask for the value inside the future. This allows that IO to be this referential transparency, because we know with futures and promises, you're contacting something in the outside world, and depending on when you ran that future, the outside world may have been different, so you hand that future to somebody, and now you're getting a different value. With IO, once it's run, or every time you run it, you will get that different value. The IO, the function that returns the IO is the referentially transparent part. We're hiding the not referentially transparent part inside of that. We're carrying that around. So I doubt that made it any clearer, but I'm hoping. Any other questions before I move on to round 2? All right. So let's talk about how to read pure functions. So let's assume from here on out, for the sake of ease, we are using our signposts to tell us if they're a dragon. So if you see IO, you know there's an effect happening. If you don't see IO, there's no side effects happening. So can anybody tell me what this function does? It has many possibilities, so just name a few.
Takes an integer, returns it.
So it takes an integer and it returns an integer, but can it do something with that integer? It can square it.
The integer somehow into another integer.
It transforms it somehow to another integer. You can add 2, multiply 10. It can do any number of things to that integer. So I can do just about anything it can do. What can this function do?
Same operations on an A and return A, whatever A is.
A is an abstract type, defined at compile time by some other calling function.
Takes an A, returns a different A or the same A.
You have no idea what A is, so you can't make a different A.
It can do all the things that A can do.
The only thing a function of this type signature can do is take the A and return that same A. It's the identity function. So if you see a function of this structure, that's all it can do. What about this one?
Take one of the A's, 2 arguments of type A and returns an argument of type A.
Okay, it takes 2 arguments of type A and returns one of the A's. It can return either the left one or the right one. Can it do anything else?
Unless there are operations defined on A.
So hopefully well, there's no operations on A because we don't know what A is. What about this one? It always returns A because we don't know what B is when we write this function. So it literally can only return A. So we have some more functions here. Trying to get some insights as how can we read type signatures and infer what the types are doing. So what does number 1 do? Takes some A and puts it into a list. It can also take some A and return an empty list. It can take some A and return a list of some size only containing that same A. So there's only really like 3 possibilities that function can do, right? What about number 2?
How do you know it can return an empty list?
Because we know how to construct empty lists, because list is a concrete type. So we can make an empty list. just with anything, right? So what about number 2? So we have a function of sum A to sum B. Or we have we have 2 parameters here. The first parameter is a function from A to B. The second parameter is a list of A, and the output is a list of B. It's a very familiar function if you've worked on, huh? It's map. So we can take each element in the list of A, call the function of A to B on it. Now we have a list of B's. So map is a familiar function that.
Why is it returning list A? Why is list A in between the return to list B?
It takes a function that converts A to B and a list of A. So the list A is an input,
Well,
and then between those two.
so that's not.
I think the signature we're looking at there is a function that takes a function of A to B, returns a function that takes a list of A, which returns a list of B.
Okay.
That is correct. We're using curried-style Haskell kind of type signature syntax, but you could also look at it as these 2 parts here are the 2 parameters to our function. The first parameter being a function of A to B, and the second parameter being a list of A, and then this is our return. The reason I'm using Haskell-like syntax for the type signatures is just when you're used to reading them, they're very compact. So we can try to elide away all the details of like def, some function name, yada, yada, yada. All right, so what about number 3? Since we figured out what number 2 is,
Reduce.
it's very similar to number 2. It's a flat map. So we can take in so we have some A that can produce a list of B's. Or that's what our function is. Given some A, give me some B's. And then I'm given a list of A, so I walk every A in the list, and that produces a list of B, and I concatenate all those together into a list of B's. Now, obviously, we could also just return an empty list, or just the first one in the list. So that's another couple possibilities of what it can do. But the most common implementation would be flat map, most useful. Anybody got any ideas on number 4? It's filter. So we can remove some elements from the list that don't meet our Boolean condition. It can also be filter not, so the inverse. We could be inverting that Boolean.
So okay. So just like in the flat map, the list B that is given is not the list B that's returned. It's a list of B's.
So the question is the list on number 3 here, is the list B here and the list B here the same list? And the answer is no, they're not the same list. We're taking each element of this list, running it through this function, and we get a list of B's for every element, for every A in the original list. And we concatenate those together to form the new list B at the end. All right, number 5. Anybody got an idea what number 5 might be?
Oh, that is reduce.
It's a form of reduce. It's the more generic case. It's fold left. The more generic version of reduce is fold. Reduce has a signature of A comma A to A to sometimes to A, but you can elide that one off as the first element of the list, and then it takes a list of A and returns A. So you'd replace all of the B's in here with A's to get reduce. But with fold, it doesn't have to return the same kind of thing that's in the list. you can think of it as you can, with a fold, with a reduce, if you had a list of integers, you're gonna get an integer out with reduce. You can add all of the elements together, multiply all the elements, etc. With a fold, the function b comma a, the function b comma a to a, the did I typo that? No, I didn't typo that. That's fine. The b can be a string, and the a can be an integer, and this b here could be, say, the empty string. And then this operation here, which, yes, I typoed that, that should be b. The b to comma a to a. I apologize. That should be a b here. But if that's a b, then we can say take the string here and this integer and concatenate them, add that integer to the string, so toString and add it, and then I get a string out the end. Just a single string and not a list of strings. I apologize for that typo there. That definitely made it more confusing. But hopefully that gave us some intuitions about how we can look at a pure referentially transparent function's type signatures and get some hints about what that function does. And I'll admit, a lot of the times when I'm looking through API documentations for libraries that I know are written in a purely functional style, I spend most of my time looking at the type signature and matching that up with, I have a shape of these things and I want a shape of this thing. How do I find a function that goes these ins to this out? I'm not looking at the names as much because some of the names are like sequence and transverse, and I'm not entirely sure what the difference between those two are until I look at the type signatures. Or do I want to fold left, or do I want to fold right, or do I need a reduce, or...
What does that mean? Does that mean at the beginning of the list or the end of the list? So this is like an array, right?
So the fold left and fold right is the direction the fold occurs. The fold left starts at the left side, and the fold right starts at the right side of the list. So it starts at the beginning or the end. That's the difference between the two kinds of folds. I don't remember off the top of my head what the difference between traverse and sequence is. I think traverse does a map, and then, yeah, I mostly just look at the type signatures, see that they match the shape of the things that I have and the shape of the things that I want.
That would be a reduce, because in Ruby you can pass an operator as, you can pass a function as a function. So like you can say, something dot reduce and pass an ampersand plus, and that will take all the things that are in there and concatenate them into the sum of all the things.
Yeah, yes, fold left is a more generic case of reduce. You can implement reduce with fold left. It's definitely, if you just change all the B's to A's, then you've definitely got a reduce here.
Well, you can use reduce the same way you can use fold left in like JavaScript.
In fact, they might use the same name instead of fold
Yeah,
left.
they just call it reduce.
In-
But there, it's because there is no type checking on that. It's just like, I don't care, it's whatever.
Yeah, and in the case of Scala collections, we have a special reduce function that is separate from the fold left. That way, in that case, you have a list of integers, and you want to just start adding them together from the first element in the list. You can just use the simpler function that takes an A to A to an A instead of this more complicated one, right? It also makes it easier to read the intent of the developer when you use a more specific function. All right, so now let's do the same exercise again, but this time we're going to pull in our signposts, that IO, that effect. All right, so can anybody tell me what this function does?
Bad things.
Could look like that. We don't know what A is, so we can't really do anything with A. In a statically typed language, that's pure, we don't know what it is, so we can't really do anything with it. So really it's just wrapping it into an IO. What about this one? It's just our IO map that we implemented earlier. It's just a way of taking the contents of an IO of A, calling the function on it, the function of A to B, and now we have an IO of B. So that's just our map. What about this one? Now note, as I'm going through these, since we don't know what A and B are, we can't do anything terrible with them. So we can't call out a database system, we can't print them to the console since we don't know what they are yet. Please ignore that Java has a toString on everything and serialize on everything. But you can't really do anything with them, right?
That would be a flat.
So this one's flat map. So some user passes in an A to IO of B, and then we transform that inner value. All right, what about this one? We now know specifically what the type of A is. We're back to our first example of A to IO of A, but I've specified that it's integer instead of some abstract A.
So now, again, we can do all the operations that you can do an integer and return.
We can do anything. We can call out a database. We can send it to an HTTP server. We can write it to the console. We can start nuclear wars. We're back to the original problem of I can see that I'm doing something outside of just doing a transformation of int to int, but I can't tell what a function is actually doing. So I guess we're now back to square one. But we do know there is an effect, and this is the important part of the exercise of trying to figure out, get this intuition of how do we read these signatures. So anybody have any questions before I move to the next part? How many people's fallen asleep? We got one in the back asleep. All right. Free food and nap time. All right. Can we do better than this simple IO there be dragons signpost? Is there a way? Is there a way? Is there a way that we can be more specific about the kinds of things the function can do? Not just a generic, there's an effect to the outside world, but a specific kind of effect. Yes, the answer is we can. Obviously, there wouldn't be a point to this talk if there wasn't. So, we're going to take a quick diversion real quick and talk about something called type classes. Who here remembers what type classes was from the talk we saw with Jordan Palmer like 2 months ago, where he kind of skimmed over that when talking about type systems? You got a couple hands up. So let's talk about what did we see similar between the list of A and the IO of A when we were trying to build up those intuitions. They had a pure function, so you can take some A and return a list of A, which means you put one A into the list. In the case of an IO, we had this ability to just stick a value inside of an IO, right? We had a map function, so we can transform the values inside of IO or inside of the list to get some new IO or some new list. And we had a flat map function. So these are just three examples of things that are in common with list and IO. So we'll say that IO of A and list of A have similar shapes, like a tuple 2, not the same shape. IO has an A, tuple 2 has an A and a B. They're not shaped alike. You can also see that there's also set and option. Can anybody else name anything else that's in this kind of list of A or thing of A shape? Futures and promises are in this kind of shape. Vector, we can talk about other collection types. Yeah, SEQ in Scala, seek is of this shape. So then we have this other shape, f of A comma B, which is like either or our tuple 2. And there's, let's see, I'm sure there are some other things of this shape. Can anybody think of anything? Validated. Works pretty similarly. We can construct our own case class and have two abstract types that meets the shape. So we can see now that we have similar shapes between some of the common things we use. They have the same shape and they have some of the same operations. If we look back, list, IO, set, option, they all have map. They all have flat map. They all have some sort of pure. But only if we can't quite treat them the same way. Option and list and IO don't have the same parent classes. So we can't just say the parent type of this is what I'm going to take into my function if I want to operate across all of them. So is there some way we can treat them the same? So we need the ability to abstract over these container types. We need to be able to abstract over the shape. And we need the ability to do something with those abstract containers. So here's our example. This is a trait in Scala. It's got this shape that we were talking about with some hole in it that we need to fill. And you can see here, when we write this map function, some A to B, we've got a function of A to B, that's what we've seen before. But this is the important part. We don't know, thank you, Philip. So you can see my F here has a hole in it that's not specified in the trait here. And we have some map of A, comma B, the function of A to B, just like we saw with our list. But the important part is, this F is abstract. We don't know at the time of building this trait what F is. We know that there's some things that fit this shape, but we don't, F could be anything, right? But we now have this, this set of operations we're gonna put in here. So what F underscore here is a higher kinded type. It's an abstract type that allows us to abstract over the container type class. This mappable here is what we're going to call it. It's a behavior. It's a type class. What you can think of higher kinded types as is you can think of them as constructors for your types. So we don't know. So F underscore you can think of as a function at the type level that takes a single parameter, and then here we're passing in that parameter. That parameter is A. We now have a concrete type. It's F of A, whatever that gets determined to be at runtime. And then here, this F of B is the same scenario. We've got a constructor, and we're putting in the parameter. The parameter is B. Now we have a concrete. It's still somewhat abstract, but it's a specific type rather than this type constructor. Yes. That's why we're in a place next to a location adjacent to the scary door. All right, so let's look at both parts of this. In the area of mathematical logic and computer science known as type theory, a kind is the type of a type constructor, or less commonly, the type of a higher order type operator. That didn't help, but it's that type constructor I was talking about. In computer science, a type class is a type system construct that supports ad hoc polymorphism. This is achieved by adding... Yeah. But we're statically type checked. All right, this is achieved by adding constraints to type variables and parametrically polymorphic types. Mappable is a type class, and I'll show you more about that in a moment. Did I hear somebody have a question? Thought I heard somebody say.
Well, I was just going to say that was exactly what I was just going to spit out.
Yeah, it's completely, Wikipedia is so great at defining it so that everybody can understand. All right, it'll make more sense when you see some code. All right, so we're implementing here a specific instance of mappable. So list is that type, is got to fill in that F slot because it has the shape of F of A. So we're going to say new mappable of list, and I should highlight on this screen, not my other one. So some new mappable of list, and we're going to delegate to the native list, the native map implementation, because why not? So we're seeing that instead of F of A, we have list of A, list of B, and we're going to do the same thing for mappable of IO. We're just going to fill in the blanks, and we're going to delegate to the map we defined earlier in the presentation on our IO object. Now, what this implicit keyword here does is in the Scala type system, this says anywhere I need something that is a mappable of a list, use this. Anywhere where I say I need something of a mappable of IO, use this one.
And these are built-ins, or are these things that you add to as you need?
Implicits are built in, at least the keyword is. And then all I have to do is make sure the implicit is imported into the scope that I need it. So
you define these as you need them.
I define them as I need them. So I can define new instances of type classes like set. You'll find that a lot of there's a couple libraries that I'll go over in a moment that include this functionality, so you will not have to write this thing yourself. but this is to try to demonstrate what it's doing, right? So anytime I need a mappable list, I will get this list mappable, and anytime I need implicitly a mappable of IO, I will get that. So I'm going to add a quick syntactic sugar helper. This just makes it where I can call map on some f of a. And I'm just going to wave my hands and say everybody understands that. So now I'm going to do this add to everything. And what I'm going to say is I have some f that I don't. I have some f that I don't know what it is. It's not a list, it's not a set, but it has the shape of one order higher kind. And I'm going to do this colon mappable business here. And this is telling the Scala compiler, hey, when somebody calls add to everything and they specify f, it must have a mappable implicit somewhere of that type that I can use. So this is using our type class.
You're specifying that it must have meet that condition, or you're
I'm
saying
specifying f must meet the constraint that it is mappable. So that is to say that there is some implicit of mappable. If it doesn't have it, I will get an error. It will fail at compile time. I will not be able to perform it. So, no, I want all my bugs. I want all my bugs at compile time. If it compiles, ship it is my mentality here. All right. So joking aside, we have some f of int, and we're going to return an f of int, and we're just going to add 2 in here, using that syntactic sugar for map that I wrote, so I don't have to write out mappable, map, blah, blah, blah. But I can say f.map underscore +2, this being syntactic sugar for a lambda that takes one parameter and then adds 2 to it, okay? So now we have this new function, and you can see the Scala compiler outputs it a little different than we write it. It adds this implicit parameter to it for a mappable of f, and it calls it an evidence. So if you don't have that mappable of the thing at compile time, it will say evidence 1 not met, and then you'll be able to see, oh, that's a mappable.
Like shell, like that's the first argument, positional argument.
Yeah, it's just an argument. In this case, it's on the second parameter list, because Scala allows multiple lists of parameters. It's kind of curried and kind of not. It's weird. So in here we're gonna say add 2 to everything. I have a list 2, 4, and 5, and you can see it outputs a list of 4, 6, and 7. And then I add 2 to everything, but this time we're gonna have a pure IO, and we're gonna call unsafe run to go ahead and execute it so we can see what the inner value is. And you can see, took 40, adds 2, we have 42. Now what's important about this, note we don't know that f is an IO, it's not specific. So that means it can't possibly call out an external database. It can't do any HTTP calls. The only thing f is allowed to do is that one constraint we put on it, which is mappable. So it can only map on the value of f. We can do anything that an int-to-int kind of function can do, and we can do it over any kind of container we want. We can do it over integers, we can do it over lists, we can do it over futures, sets. All we can do is map, though.
Can you then add another like runnable or Darrenable or some other thing?
You're skipping ahead on me. All right, but the answer is yes, but we'll get to that. All right, so can you guess what the common name of mappable is? Maybe not the common name, but the category theory name. It's called functor. So functors, there's a lot of category theory laws and baggage and overhead on what a functor is. It's not enumerable, but there's a lot of baggage of what a functor is, and I could go to Wikipedia and pull up the definition, and it would make all of us go glazy-eyed for a moment, including myself. But the intuition is a functor is just a thing that you can map on. It's a thing with a map function. And we have a whole group of these things that we can leverage. So there's more than just functor. There's other of these type classes, of these behaviors, of these constraints that we can apply to our higher kinded type, our f. And this is where I pull up. Let me see if I can make my slides behave, or make this behave for a moment while I pull this up. Let me zoom out.
This is CATS, the Scala library.
This is the CATS infographic. the cats library in Scala, which is the category theory library. There's a similar library called Scala Z, and there's a couple other ones. Cats is the one we just use on my team. You can see here's functor that we were talking about. You've probably heard me use the term monad before. Only when I'm angry. But there's all these different type classes, all these different behaviors, these constraints that we can apply to our F. So we've got this reverse, we've got foldable. So this gives us that fold behavior that we saw on lists. We can apply that to other things abstractly by giving it the foldable constraint. Applicative takes a functor and just adds that pure function to it. Because functor, all it can do is map. You can't put anything inside of it. But if you have an applicative functor, you can now put something inside of the functor and then later perform a map on it.
So an applicative from the tail and head there is a functor that has the apply category as well?
Yep.
Alright, so what are the purple ones? Those are like current categories?
So these are just marked colored so you can see which cat's library it comes from.
Oh,
Because Scala Z is like everything and the kitchen sink kind of library. It has all of these functions in it. But cats tries to be more pared down, more specific to,
a la carte.
yeah, you pick what things you want. There's the MTL, there's effect, there's the kernel, which is the smallest part of it all. This stuff up here at the top is the kernel. So it tries to let you pick and choose which parts you want. So now you can see applicative is an apply is a functor, and you can see here, monad is an applicative is apply as a functor. Here's that flat map. So we can say all of the things that have a flat map, we can put that constraint on there. But if you're a flat map and you're an applicative, you're probably a monad. So the intuition I'm trying to give you is if you have the monad constraint, you have a map, you have a flat map, and you have a way of putting a value into it. You have a pure. Okay? Now, remember that IO type we demonstrated at the beginning, that signpost, that thing we use to indicate that you can suspend some effect for later happening. That is a sync, some synchronous effect. With the cat's effect library, we also have one called async, an asynchronous effect, something with a callback. Those are your futures, your promises. And in cat's effect, there is an IO type that's similar to what I have, but has the ability to do asynchronous stuff, cancellations, racing two effects together, bracketing, resource management, etc. So we have concurrent, effect. These are all constraints that you can apply to that F type. And importantly, by applying, even if you wanted to use an IO, you knew you were going to do something asynchronously, rather than specifying it's an IO, if you specified it's an async or it's a concurrent, you can substitute in other versions of IO. You could use something like Scala Z's task instead, because it can meet those constraints. And maybe Scala Z8's task is more performant than cat's effect IO. You'd be able to make that choice at the top level of your program instead of at every step and then have to refactor everything like I literally had to do to 5 APIs at one point. So being more abstract can save you a lot of rewrite time later down the road. Because we literally did switch out using Scala Z to using cat's IO on Scala Z7. It sucked. It was a lot of... All right. Yeah, it was... You made me do it all. All right, so far what we've learned is we've learned what effects are. We've learned how effects can be bad if you can't tell they're happening. We learned how to reason about a function from its type signature, and we learned roughly what a type class is and somewhat how to use it. So we should have some intuitions at all. So now that we have the tools, let's F it all. Just talk about Finally Tagless here. This is a technique in functional programming that comes from Haskell. There's some competing techniques like the free monad that we're not going to go into because I have 10 minutes left of your time. But the Finally Tagless is the style that we use on our applications. I can't say production because one of those haven't gone to but in a non-production environment that will soon be in our production environments. So this is a technique I actually use in my day job. Yes. All right. Let's see some code though. And this is where I'm going to futz with my displays and hopefully not make Blixa cry.
All right, I'm ready to see some food you've done.
Blixa, did I make you cry?
It's fine with me.
All right.
It's working.
Let's see. All right. What we're going to do is we're going to define a class. Well, first I'm going to import a bunch of stuff. Pay no attention to the man behind the scary door. We got some cats. We got some cats effect. We got some cats MTL. We've got this log for cats. We've got this library here. This is just saving me work, so I don't have to redo it and show you guys how that all works. So let's put that behind us. Let me, though, save all of our eyes from squinting and try to get IntelliJ to do in begin mode. Hopefully that's more readable. Okay. So we're going to define some user, and yes, all these examples are contrived because I didn't want to show off proprietary code. So we have some user, has a name. He has a name, an age, a country, or she. We have some algebra we're going to define, and we're going to define it as taking some f. We're not going to put any constraints on it. This is as abstract as it can be. We're literally not even implementing it. We're just saying we have a create, and we have a find by name. The create takes in all the things and gives us out a user. The find by name gives us an optional user, so the user may or not exist. This app type class is just doing, remember when I wrote mappable and I did that syntactic sugar? This does that for me and gives me a way to summon the type class, and it saves me a little typing. So it's hiding some of that, doing the boilerplate automatically for me using a macro. We have this country algebra. It's going to be the same way, and it's going to look up the voting age by country. And then it'll give us an optional int. So the country may or may not be in our database, or may or not have a voting age because it may be some sort of terrible dictatorship with nuclear weapons. All right, so let's implement a country algebra, and we're going to put one constraint on it because this is for testing purposes. We're going to give it the applicative constraint. So all we can do is put a thing into the f. All we got is a pure and a map. And in this case, we're just going to use pure. So we define our country algebra, we define our voting age, and it's really just going to go look at the country. If it's USA, we return 18. If it's Canada, we return 18. If it's Brazil, we return 16. If we couldn't find it, we return empty. And this is... I wrote them differently to show the syntactic sugar. This is the same as this. And so this pure of f is just a way of calling this applicative f dot pure and then putting the value into it. So I can write option dot empty int dot pure. So I'm just kind of showing off some of the weird syntax that you can sometimes get in Scala and the 15,000 different ways to do the same thing. So this is our country algebra. Do we have any questions on its implementation? I think it's pretty bland. Doesn't even have a database. But it's still abstract in its f so that we can compose it. All right, now we're going to define this function, find or create user. We're going to give it the monad constraint, and we're going to give it the user algebra constraint, and we're going to give it the message logger constraint, so that log for cats. Message logger is just a way of taking a string and outputting it to something. It's abstract. We don't really know what it's doing at compile time, or at least at this part of the compile, right? So we then take our name, our age, and our country, and we go to our user algebra. We try to find it by the name, and if it exists by name, we're going to write out to our message logger, we found the user, and then we're going to stick it back in F and hand it off. So this way, if we have some sort of effect in our message logger, we can manage that effect. Then we're gonna do, if we didn't find it, if the find by name came back with a none, we're gonna call create, and then we're gonna log that we created that user. So this again is just a syntactic sugar for doing a flat map. This just says ignore the return value of the thing on the left, and do the thing on the right and return its value. And then this one is much similar. It's take the value of the thing on the left, but still do the operation of the thing on the right. but forget the thing on the right's value, we don't want it. There's similar operation for do both things and put it in a tuple forming. So these are common operations, which is why they made a symbolic syntactic sugar for us. All right, so we can look, if we didn't have this implementation though, if we covered that up, you can see from our F that we cannot do inside of find or create user. We can't do any database operations, can't do any external calls. So we're pretty limited by what we can do inside of it. Let's look at isVoter. isVoter gets a country algebra, gets a user algebra, and gets a message logger. And we're gonna do a similar thing. We're gonna call the find or create user, we're gonna give it its stuff. We're gonna go try to find the user's country, and get its voting age, and we're gonna compute a yes, no, or I couldn't find the country, no idea. And then we're gonna return that. So we see its constraints. And then here's program. It's just got monad, country algebra, message logger, and user algebra. So it's got all the constraints we just developed, but still doesn't have a sync constraint. So
You have to relist the constraints for the program. So like monad, even though
because it's calling isVoter, and isVoter has these constraints, I have to provide it the same level of constraints.
okay, it won't pull them from the.
Correct. If I instead set up program to take in a function like isVoter that had these and return an F, I wouldn't have to have those constraints on here. isVoter would still need those constraints, but program wouldn't be operating on isVoter, it'd be operating on some function coming in. And whatever that function's constraints were, it wouldn't have to have, just what it's using internally. But somewhere at the top level of the system, we're gonna be like, we have all of these constraints for our overall program. The whole program does things with monads, with country algebra, with message, and with user algebra. So here we're just gonna check if Tim is a voter, check if John is a voter, and then check Tim again because we got Tim twice. And then we're gonna yield out those three values. So it's contrived, it's relatively simple, but we can see the constraints. So we're gonna go through the exercise of defining some of these algebras and then showing what the outputs are. So here we're gonna do I have some variable that's mutatable, some outside state, and I'm gonna define a user algebra that operates on that. I'm gonna call it a database. This is not actually calling a database because that would have taken a long time to hook up. We're gonna say create just takes the user you passed in and adds it to that map, and it delays that effect inside of that sync. So we know from the constraints of DB user algebra that it can't hit a remote system because it can't do an asynchronous call, but it can do something synchronous, so it can mutate some local variable state or something. So it's still doing an effect we want to manage. We now know that there is an effect here. And then the find by name just does the same delay on it and then goes to that map and gets the value. We're also going to define this console logger, which I implemented, and I don't know if I can command click in. Yeah, we can. So all this does is it delays the effect of printing it to the console. And of course, since it's a logger, we have a whole bunch of different ways we can print it out. Now I'm gonna run the program and I have to explicitly say, hey world, I'm ready to do the unsafe thing. We're gonna call unsafe run sync in the case of IO. We're gonna tell program your F is IO. And so it will return the IO of the things we wanted. And then I'm gonna print out my fake database. And we can see we logged created user Tim. We logged created user John. We logged that we found the user Tim, and yeah, it's a little redundant. I didn't look on my two strings well enough. And then here so there's the effects of logging, that print line effect that we managed. And it only happened after we ran that. If I take that off and run it again, and yes, I am aware, Blixit, that I'm a little over time, but we're getting close to the end. So if I take off that unsafe run and then wait for the Scala compiler, there we go. Scroll back down to where I was. You can see that in this block, there's not effects anymore. All we got is this, I printed fake DB contents. I didn't do anything. So I constructed the program, but I don't do anything until I call the unsafe run sync. Now let's look at this next example. DB algebra, I'm changing the constraint. I'm only got a monad constraint. But I have this implicit monad state. So remember earlier when I was talking about type classes and I said there's two ways to write it. There's the colon syntax like this, but there's also an implicit parameter. We're doing an implicit parameter. This monad state comes from the cat's MTL, and it says, I have some monad, I don't know which specific one it is, but it has the characteristics of a state monad. So it's still abstract enough that I can specify, I can make my own state monads, I can do all sorts of crazy stuff, but this function doesn't have to know about any of that until later. So we're gonna say that the monad state contains in its state the map of string the user, and we're gonna modify the contents of that state here and get the contents of the state there. Then down here, we're gonna create our writer, and it's gonna be part of this monad stack. So we got our state T and a writer T on the ID. Writer's got a list of strings, and state's got a map of string the user. So we still got the same kind of database that we had in our previous example. It's a map of string the user. But we don't mutate a variable here. State manages that internally. When we go to run program and we tell it our monad state, when we run it, we need to give it the state that it starts with, and then we need to call run to do the execution. This is not a run sync, this is still referentially transparent. If I hit run twice on this program, I will get the same exact results. We don't have a sync constraint. I will get the same results every time. Now my output is going to contain this log, this list of string from the writer T. That's coming from our writer log implementation, which I'll pop over here. This is using a functor tell, which is part of MTL, but it's just a way of logging out the effects into our monad stack. So we have our logs, we have our user DB, and then this is the actual output of our program. So I can print off my logs, which I think my right-hand side of my screen got out of sync, so I'm gonna click play there. I don't see.
You scroll up.
Oh, okay. So you can see my logs. As I'm printing out logs, make string, created user Tim, created user John, found user. Note I didn't print to the console for any of those. I wrote the values to the writer T, and I didn't have to change program. I just changed the type class behaviors that I was passing to the program. So it's sort of a dependency injection, but because we have higher kind of types, it's a bit more powerful. Then I printed out my user database here, and then this is the output of the program itself, each one of those users. All right, so here's the final example. And the reason why this is so important is when you're writing tests, you don't often want to be thinking about asynchronous side effects. You don't want to be thinking about synchronous side effects. You just want simple inputs and outputs. So I'm defining a user algebra. We're not going to do a create this time because I was lazy, so we didn't implement it. But I'm just going to stick name in it as a pure value. I'm going to use the no-op logger, so I'm not going to bother testing logging. This literally does nothing. We're going to use the ID monad here. And the ID monad is literally, it's defined like this. It's type ID of A equals A. It's just do the value. It's as simple as that. So when I define my DB user algebra, I'm passing in my database as it will be the entire run of the application. Then I execute my program and I print out my 3 users and I get the same results. But I didn't log this time, I didn't create because I cheated. But when you're testing, sometimes you can cheat a little bit. So this is how, hopefully this kind of demonstrated how we can use higher kind of types with type classes to define these algebras that we can then compose together in our total program. And we can define these constraints in such ways we can read what a program can do without giving it the ability to just do everything. And now we can get some insights on what it's doing. And we can switch out the underlying F at any point for some other kind. Finally, questions? All right, thanks for coming. Here are some references. If you would like, LambdaCast, excellent podcast on functional programming. It covered some of the stuff about reading types of functions to figure out what they do. I highly recommend, and I know it's 2 hours of your life, but John DeGoes has a YouTube video called FP to the Max that he did for some other functional programming group, where he sits down and he takes a toy example of a program and he It's an imperative program, simple example, and he cranks the dial of FP up to 11. He does the crazy stuff that we just did, but explaining every step of his methodology and live codes it so that you can see and understand what he's doing and why he's doing it. And I don't pretend to be as good of a orator as him, so I highly recommend watching that. Also reading his podcast or reading his blog, because he has some really crazy stuff to say about how concrete variable names are code smell and other interesting clickbaity topics. And then there's this article series that I found, Types Never Commit Too Early, that kind of goes through the process of working up to these finally tagless algebras that we just talked about. Any other
Why is
questions?
it called Finally Tagless?
Good question. Any other questions? Now, it comes from a paper written in like the 90s. It also goes by Tagless Final. It has to do with the way that Finally Tagless works in comparison to a free monad. Free monads tag your values at runtime by wrapping each step, and then you have to basically loop over and unwrap the values executing each step. So you have to have an interpreter, whereas Finally Tagless doesn't have this runtime tagging. Consequently, Finally Tagless is more performant than free monad interpretations because of that value wrapping that you have to do with free monads. Free monads are pretty easy to optimize though, because the values are wrapped, and so you can just like cache steps of it and do all sorts of crazy runtime optimizations that you can't, like cache calls to the database automatically by just writing an interpreter that does a caching step. And there's some weird stuff you can do. You can do those things in Finally Tagless, but it's a little more work. But because Finally Tagless doesn't wrap each step in the same way, you don't get this additional wrapper. It's far more performant to do Finally Tagless. Also, I think that Finally Tagless is a little more intuitive to an object-oriented programmer than free monad, because with Finally Tagless, you write these traits, these type classes that have methods in them, and then you can new up and implement those methods for specific F types, or at least to some extent abstract versions of that. Whereas with free monads, you're defining a bunch of these case classes that represent each kind of computation you're doing, and then you have to write this thing that takes in the parent, you use an ADT, and you gotta take in the parent, and it's a whole thing. If you wanna know more about that, there's a lot of great talks online. The Doobie library, which we use for working with database calls, it uses a free monad and interpreters to do database. And I think because it does that, it has some kind of brilliant characteristics. And because databases are inherently, JDBC is synchronous and has some overhead already, free doesn't add that much to it. And so in that case, it's great. But when you're talking like applications that I write where you're doing HTTP stuff with a lot of async calls out to a bunch of systems, free kind of adds a little bit of memory overhead I didn't want to take on. Also the cognitive load, that's the big one. So, but yeah, I don't really know too much details on why it's Finally Tagless or Tagless Final and not something else. Any other questions? All right. Thank you again, everyone, for coming. Thank you, Tech Systems, for food. Always appreciate it. Next month, we should be doing a talk on continuations by Jonathan Bartlett. So hope to see you guys then. I should get the meetup posted in a couple hours so you can RSVP so we know how many people is coming.